Hokey dokey. All right. Welcome to BIT 2406, Chapter 2. All right. In this problem, they say that we have a fertilizer company making fertilizer. We have two chemicals that provide nitrogen, phosphate, and potassium. A pound of one contributes 10 ounces of nitrogen, 6 ounces of phosphate, whereas a pound of ingredient 2 contributes 2 nitrogen, 6 phosphate, 1 ounce of potassium. Okay. Ingredient 1 costs this much, ingredient 2 that much. They want to know how many pounds of each to put in the bag to meet the minimum requirements of 20 ounces of nitrogen, 36 phosphate, and 2 of potassium, minimizing the cost. Okay, so let's start with minimizing the cost. Usually the thing we are finding a max or minimum of is called Z instead of cost. Okay, but Z represents cost. Ingredient 1 we will represent with, let's see how they do it, X1s. Yeah, so we have X1 is ingredient 1 and X2 ingredient 2. So ingredient 1 costs $3 per pound. So we're going to go, the cost is 3 times X1 plus the cost of ingredient 2, which is $5 per pound of ingredient 2. So the cost, the thing we're minimizing, is Z equals 3x1 plus 5x2. Now, we have some constraints, and that is we have minimum requirements of 20 ounces of nitrogen. So we think about this, we need at least 20 ounces of nitrogen, right? So we're talking greater than or equal to 20 nitrogen. So we're going to do a little nitrogen equation here, or inequality. And so we think about ingredient 1 has how many ounces of nitrogen? Well, it has 10 ounces of nitrogen in ingredient 1. And then ingredient 2 has 2 ounces of nitrogen. So talking 2x2. Yeah, okay. So 10x1 plus 2x2 is the total ounces of nitrogen, right? And yeah, that's it. Okay, yeah, just making sure I have this right. Yeah, okay. Yeah, we're good. So that's nitrogen. Now let's do phosphate. Same deal. Very similar situation here. So ingredient 1, 6 ounces of phosphate. Ingredient 2 is also 6 ounces of phosphate. So we're talking 6x1, 6x2. And they say we have to have a minimum of 36 ounces of phosphate. So greater than or equal to 36. Okay. Now the last one, potassium. And you'll start to see the answers here. I had them close by so we can compare. Potassium, ingredient 1 has no potassium, right? So 0x1 essentially, plus 1 ounce of potassium in ingredient 2. And that has to be greater than or equal to 2 ounces of potassium based on the minimum requirements, okay? So we can really get rid of the 0x1 because 0 times x1 is just 0. What am I forgetting? That might be it. That might be all I have here. So we're minimizing this, minimize cost, and these are our constraints. All right, let's see what they have. So minimize this. That's the cost. Checks out. Everything else looks solid, and I guess just the fact that x1 has to be greater than or equal to 0, and x2 also has to be greater than or equal to 0. It's just stating that like the number of pounds cannot be a negative number. Okay, and then they say solve this model by using graphical analysis. I will not graph these. You could graph these in Desmos and do a whole thing, or in Excel, whatever. But I'm just going to explain their graph, okay? I got a lot to go through here, so I'm just going to make sense of it, okay? I'm going to do a good job of making sense of it, though. So each line and each dashed line that you see here is one of the constraints that we just wrote out, okay? So let's see if we can identify what's what. So if we think about, say, this first one, 10x1 plus 2x2 is greater than or equal to 20. Imagine we calculated the x and y intercepts for that inequality. By x and y intercepts, I really mean like the x1 and x2 intercepts. So if we ever want to find the x2 intercept, notice the graph here. The x2 is like the y. If we want to find the x2 intercept on the x2 axis, we set the opposite variable, x1, equal to 0. And so still looking at this inequality here, right? We plug in 0 for x1, and we are left with 2x2 is greater than or equal to 20, and then we divide by 2, and we get x2 is greater than or equal to 10. So what I'm trying to say is like x2 equals 10 is your x2 intercept, which we see that right there. And then we repeat so right here. And then we repeat the process, and we plug in x2 equals 0 to solve for the x1 intercept. So still looking at this inequality, if we plug in x2 equals 0, we're left with 10 x1 is greater than or equal to 20. Divide by 10, we get x1 is greater than or equal to 2. So the x1 intercept should be 2. And so of this line, that's why we see this intercept way down there. Okay, so this line is most definitely this constraint, okay? And because it is greater than or equal to 20, that's kind of an indicator that if we just had this line here, this red line, we would be shading above that line. I know it looks like it's to the right of that line, but it is above that line as opposed to below it in that little skinny triangular area, okay? So that's the first line, and I'm going to speed up the process here. You can probably take a nice guess and say that this second constraint is going to produce this solid line from 6 to 6 on each axis, right? Then same argument, because it's greater than or equal to 36, that's why we're shading above this line as well. And then what's next? We have x2 has to be greater than or equal to 2. And that's actually this horizontal line right here. That's just like saying y is greater than or equal to 2. So we have a solid line along x2 equals 2 or y equals 2, but it's shaded above it because x2 has to be greater than or equal to 2. Now the dash line, what the hell is that? Maybe the dash line is just that's probably something else. That's probably from, I don't know, I think I'm drawing a blank here. So that's somehow that's somehow like the cost equation in some form or another. I don't know, something along those lines. Anyway, I'm just going to tell you what I know here. So once you graph those 3 lines, I guess like the 3 red lines I've drawn here, there's some intersection points that kind of act as your critical points here. Really just the A, B, and C there. So A, B, and C are basically points you want to test at this point. So there are points in the form of like x1 comma x2, just like x comma y. They're ordered pairs, and they are special ordered pairs that are like potential locations of where the cost will be at a minimum, or anytime you're doing this problem, you're looking for a max or a min. These points are like your special critical points where you might have a max or a min. Okay, so we test these points out into the z equation, right? And it turns out when you plug in point A, 0, 10, you get 50. Point B, 1, 5, you get 28. And point C, 4, 2, you get 22. And so, again, we are looking for the minimum cost, the minimum z value. So it turns out that point C creates our minimum cost, meaning point C is the optimal point. Okay, that's about everything I know about that one. I hope that helped a little bit. I'm going to do my best to keep it pushing here. Let's go. All right, number 7 and maybe number 8. We have coffee cakes, Danish pastries, large pans, flour, sugar, 25 pounds of flour, 16 pounds of sugar. Demand for coffee cakes is 5. 5 pounds of flour, 2 pounds of sugar make coffee cakes. 5 pounds of flour, 4 pounds of sugar make Danish. Pan of coffee cakes has a profit of $1. Pan of Danish, profit of $5. All right. Shout out to whoever that was, Pedro something. Determine the number of pans of cakes and Danish to maximize the profit. So let's start with the profit equation. We'll call it Z. Again, we'll call X1 cakes, coffee cakes, and X2 Danish. And so to be more specific, it's the number of pans of cakes and pans of Danishes. Okay? And so the profit will just be 1 times X1 because the coffee cakes have a profit of $1. So the number of coffee cakes times $1 will give you the profit for all the coffee cakes, plus the profit for the Danishes, which is $5 times number of Danish pans. So we are maximizing the profit. We're finding where this is at a maximum within the constraints that we have. So what do we have constraints on? There are 25 pounds of flour, 16 pounds of sugar. Okay. 5 pounds of flour, 60 pounds of sugar. Okay, got it. All right. So if 5 pounds of flour, so it looks like for coffee cakes and for Danishes, 5 pounds of flour is required. 5 pounds of flour is required. So we have 5x1 plus 5x2. Again, I'm dealing with the flour. And it says they only have 25 pounds of flour. So we can use up to 25 pounds of flour. So less than or equal to 25. Now we do the same thing with sugar. So we have 2 pounds of sugar for coffee cakes, 4 pounds of sugar for Danishes. So 2x1 plus 4x2 less than or equal to the amount that we have of sugar. So that's 16. So less than or equal to 16 pounds of sugar. Can't forget the demand. They say something about the demand for coffee cakes. Coffee cakes is X1. The demand is 5. And so I think the argument there is like, if the demand is 5, it's like, it's going to be no more than 5. Like, you don't want to make more than 5 if the demand is only 5. So we want to make less than or equal to 5 coffee cakes. And then they'll probably just throw in like X1 and X2 have to be greater than or equal to 0. Let's see how we did. We have the answers here. So number 1, or like part, what am I saying? The profit, the Z, we have 1x1 plus 5x2. Yep. We have the flour. Looks good. The sugar. We have the demand for cakes. Yep, and we got that. We nailed it. Okay. So now, again, with the graphs, solve this model, graphical analysis. Again, they have just graphed every single one of these things here, these constraints. Now, an important difference to the last one. Notice, all of these constraints, it was a lot of like greater than or equal to values, and so that indicated that we shaded above these lines. For these ones, it's a lot of less than or equal to. Less than or equal to. So we are going to see a lot of shading below these lines. So we'll graph the lines the same way. You treat them like, y equals mx plus b, or like x1 is x, x2 is y, whatever. You can find your intercepts like we talked about earlier, whatever. First constraint is probably the 5 to the 5 here. So this first line. Second constraint with the 2 and the 4 and the 16. I'm going to take an educated guess and say it's this 4 to the 8 one here. We can see that x1 has to be less than or equal to 5. That's this vertical line here. And again, everything's shaded either like below, or for this vertical line, it's shaded to the left because it has to be less than or equal to 5. Anyway, so we get this shaded region here, and we pay attention to the intersection points. So where they say A here, they're talking about, obviously you can see it better now, this point A, and then this is B, and then this is C. So all these intersection points are the important, like critical points that we want to test in our profit equation, and we are trying to maximize profit. So we can see that the highest Z value of all of these here is the 20. So that shows us that point A is optimal. In like, what am I trying to say? In other words, A is the ordered pair, or the number of cakes in Danishes, pans, that give us the maximum profit. Sorry, my brain is like a mile hour right now. Hope that makes sense. Let's see if is there anything on number 8. I don't think I have an answer for number 8. What do they say though? How much flour and sugar will be left unused if the optimal number of cakes and Danish are baked? Okay, so the optimal number is what? The optimal number was 0 and 4, so 0 cakes, but for a Danish. So if they made 0 cakes, they would be using 0 pounds of flour and sugar for the cakes. But if they made 4 Danishes, well, each Danish pan requires 5 pounds of flour and 4 pounds of sugar. So that's each pan of Danishes. And if we're making 4 pans of Danishes, well, that's 4 times 5 for the flour and 4 times 4 for the sugar. So they'd use 20 pounds of flour and 16 pounds of sugar. So that's how much they'll be using. And how many pounds did they have to begin with? They had 25 pounds of flour and 16 pounds of sugar. So they will still have 5 pounds of flour left over, but only 0 pounds of sugar left over. They are using all 16. Okay. That was number 2, or number 7, or whatever the fuck it was. All right. Do I want to do this in the same video? Nah. I'm gonna save this for another video. All right.